A parallelogram, the properties of a parallelogram, and ways to prove that a quadrilateral is a parallelogram. We now look at the two types of quadrilaterals, namely the convex and the concave quadrilateral. Now remember, a quadrilateral is any four-sided polygon. Here we have two sketches of the convex and the concave quadrilaterals. Let us just look at the properties. So if a quadrilateral is convex, then there will be no outside diagonals. So if we look at quadrilateral ABCD, then of course the diagonals is a line segment connecting two opposite angles. So the first line segment, or the first diagonal, is the diagonal AC, and the second one the diagonal BD. And both these diagonals lies inside the quadrilateral, so there's no outside diagonals. While in the case of a concave quadrilateral, what do we find here? Let's call it EFGH. So therefore the first diagonal will be the line segment FH and the other one EG. And now we notice that the diagonal EG lies outside this quadrilateral. Furthermore, we notice that one of the angles here is greater than 180 degrees, or one of the angles is a reflex angle. Obviously, there can only be one, at most one reflex angle, because otherwise the sum of the interior angles, as we will see in the next slide, will exceed 360. Let us see what we can learn about the sum of the interior and the sum of the exterior angles of a quadrilateral. Now assume we have the quadrilateral ABCD, and we draw one of the diagonals, say AC, and we label the angles as indicated here. Now what do we know then? Well, firstly we see we have now divided the quadrilateral into two triangles. And we know from previous discussion that the sum of the interior angles of a triangle is equal to 180. So therefore firstly we can say, if we look at triangle ABC, then angle 1 plus angle 2 plus angle 3, that sum will be equal to 180 degrees, because it's the angles of a triangle. In a similar way, the sum of angles 4, 5 and 6, being the interior angles of triangle ACD or ADC, will also be equal to 180. So therefore, if we regroup this, and I'm going to regroup 2 and 4, and 3 and 5, for the simple reason the sum of 2 and 4 is angle A, and the sum of 3 and 5 is equal to angle C. So if we add all these 6 angles, so angle 1 plus 2 plus 3 plus 4 plus 5 plus 6 is therefore 360, or twice 180 degrees. But then, instead of writing it in that order, we will group angles 2 and 4 and 3 and 5 together. So if we attach the names to that, angle 2 plus 4 is angle A, while angle 1 is angle B, 3 plus 5 is angle C, and angle 6 is obviously angle D. So here we have a clear indication then that the sum of the four interior angles of any quadrilateral will always be equal to 360 degrees. Now what about the exterior angles? Now firstly you must make sure that you understand what is an exterior angle. For instance, if I look at angle 1, then it's the exterior angle at the vertex E. Now how do I obtain it? Well, I can either produce FE and then look at the adjacent angle, or I can produce HE and then determine that exterior angle. So I've indicated the 4 interior as well as the 4 exterior angles. Exterior angles is indicated here in red. Now, what do we note? We note that the sum of angles 1 and 5, 2 and 6, or 3 and 7, or 4 and 8, all these pairs are actually form straight angles. So we have 4 straight angles. So therefore the sum of the 4 indicated pairs here will have a total sum of 4 times 180, because it's 4 straight angles. Now we want to get an idea what is the sum of angles 1 plus 2 plus 3 plus 4. So we simply regroup. So I put all the exterior angles together and all the interior angles together. Already we know that the sum of the interior angles, namely angles 5, 6, 7 and 8, is equal to 360, or twice 280. So I can replace that particular sum of angles 5, 6, 7 and 8 by 2 times 180. And what will that give us? It will then give us that the sum of the 4 exterior angles, namely angles 1, 2, 3 and 4, will be 4 times 180 minus 2 times 180, or this particular sum of the exterior angles is therefore also equal to 360. You can follow this procedure for any polygon, for instance a 5-sided or a 6-sided, etc. I would challenge you to try and explore this and see if you can firstly, for any polygon, whether it's got 5, 6 or 7 sides, determine what is the sum of the interior and what is the sum of the exterior angles. Let us look at the definition of a parallelogram. A parallelogram is defined as a quadrilateral, in other words a 4-sided polygon with both pairs of opposite sides parallel. So if I make a sketch, there's only 2 pairs of opposite sides, namely AD and BC is the one pair, while the other pair is AB and DC. And we know from the definition that both these pairs must be parallel. So in other words, line segment AB is parallel to line segment DC, and line segment AD is parallel to line segment BC. So in other words, if somebody tells you that a quadrilateral is a parallelogram, then we know immediately that both pairs of opposite sides will be parallel, and this will be actually a way to prove that a quadrilateral is a parallelogram. So therefore a quadrilateral is a parallelogram if you can prove that 2 pairs of opposite sides are parallel. Let us look at a summary of the properties of a parallelogram. Now in this sketch I tried to summarize all the properties of a parallelogram. Now remember, at this stage we only know that a quadrilateral is a parallelogram if 2 pairs or both pairs of opposite sides are parallel. So all these properties can be deduced from this definition and of course proved from the definition. So the initial starting place is with the definition, where we know that it's a quadrilateral with both pairs of opposite sides parallel. The first property that we can prove is that both pairs of opposite sides are not only parallel but also equal. So in other words, we can prove that line segment AD, the length of that is the same as the length of line segment BC, and also that AB is equal to DC. See, if I talk about AB, I mean the length of line segment AB. The second property, that we can also prove that both pairs of opposite angles are equal. So in other words, we can prove that angle A is equal to angle C, the two red ones, and that angle B is equal to angle D. At this stage, we're just mentioning it. We still need to prove it. The third important thing is that we can prove the property that the diagonals bisect each other. So in other words, if you draw both the diagonals and you find the point of intersection or the midpoint of the diagonals, then this point E will not only be a midpoint for diagonal BD but also for diagonal AC. Another property which is really obvious is that if you draw the diagonal BD, then triangle BAD will be congruent to triangle angle DCB. So in other words, the diagonal will actually bisect the parallelogram in two congruent triangles, and we know congruent triangles will have the same area. So in other words, it will divide the area, or any diagonal will divide the area of a parallelogram. We will now proceed to prove the property. So we look at the first property, namely that pairs of opposite sides are equal. Just remember, as a starting point, we only have the definition. So we are only given, we have a parallelogram. So in other words, we only know that two pairs of opposite sides will be parallel. What must we prove? We must prove that AD is equal to BC and AB equals to CD. And to prove this, we draw the diagonal BD. And all we really do is we focus on triangles ABD and CDB. Note at this stage the order in which you write the vertices here are not that important, but when we get to the end that the two triangles are congruent, the order must be spot on. So what do we see? We firstly see that angle ADB, which I've indicated in blue here, is equal to angle CBD, the other blue one. For what reason? Well, they are alternate angles because we know that line segment AD is parallel to line segment BC. In a similar way, the two red angles, as indicated here, will also be alternate, but the reason now is because line segment AB is equal to line segment DC. Remember, when you talk about parallel lines, you also need to be able to identify the transversal. If I look at line segment AD and line segment BC being parallel, then you can see that I've utilized BD as the transversal. I could just as well have used AC as the transversal. Furthermore, BD belongs to both these triangles, so therefore it's a common side. So now if we look at our congruency conditions, then we can say that triangle ABD, and now the order is important. The order here is the one that I haven't shaded, to the red one to the blue one is congruent to triangle, the one that's not shaded, towards the red one, which is D, and in the blue one, B. So the order here is very important, and the reason why these two triangles are congruent is because we have two angles and the side of the one equal to two corresponding angles and the side of the other one. And from this we can make certain deductions. We can firstly say that AB, note A and B lies in position 1 and 2, will be equal to CD, because it also is in position 1 and 2. So AD equal to BC. Furthermore, AD, now AD is in position 1 and 3, and CB is also in position 1 and 3. So AB equal to CD. So therefore we've proved that if we start with the fact that we have a parallelogram, in other words only two pairs of opposite sides parallel, we can now prove, we have proved now, that opposite sides is not only parallel but also equal. You see, from now on we can accept this as a new fact. We can accept that if we have a parallelogram, then the opposite sides will also be equal in length. But you first need to prove it from the definition. Next we prove the second property, namely that pairs of opposite angles are equal. So again, we know we have a parallelogram, so we assume therefore that we only know that the two pairs of opposite sides will be parallel. What we want to prove, see, that's what's given. It's required to prove that angle A is equal to angle C and angle B equals to angle D. As before, I construct a diagonal, thereby dividing this parallelogram in two triangles, namely triangles A, B, D, the one at the top, and triangle CDB. Now what you see here is what I've done earlier. We can firstly see that angle ADB, in other words the blue one here is equal to the blue one here because they alternate angles, simply because line segment AD is parallel to line segment BC. In a similar way, the two red ones will be equal in measure because again they alternate, and because line segment AB is parallel to line segment DC. Remember, you need to write the reasons, and of course, as we've seen before, BD is a common side. So in exactly the same way as in the previous one, we now can conclude that the two triangles must be congruent because we have two angles and the side of the one equal to two angles and the side, corresponding angles on the side of the second one. And what can we then conclude? We can conclude that angle A is equal to angle C. Can you see it's really the two unshaded ones? Furthermore, I can also conclude that angle B, now note angle B is the red one plus the blue one. You can just look at the names. Now this red one is equal to the red one up there, and the blue one here at the bottom here is equal to the blue one there, and that gives us angle D. So by using that, we can then show that firstly, straight away A is equal to C and angle B is equal to D. And now we have proved that if we are given a parallelogram, then the opposite angles are equal. Again, this can be utilized in applications, and we can say that because it's a parallelogram, we know that opposite angles are equal. Let us look at the proof of the third property, namely that if we have a parallelogram, then the diagonals bisect each other. So again we have a parallelogram, both pairs of opposite sides parallel. We need to prove that E is the midpoint of AC as well as the midpoint of BD, or another way of writing it is to say that AE is equal to CE and BE equals to TE. So in this case the construction is to construct both the diagonals, and what we're going to do is we're going to compare triangle AED, so the top one, with triangle CEB. Now what do we know? We know that AD is equal to BC. Remember, we have proved that the opposite sides in a parallelogram will be equal in length. You see, here I utilize something that I've proved. Furthermore, angle AED is vertically opposite to angle CEB, and the two blue angles, there's their names, is alternate angles and therefore equal, because we know that line segment AD is parallel to line segment BC. So therefore the two given triangles, namely AED and CEB, will be congruent, because two angles on a side is equal to two corresponding angles on the side of the other one. So what can we then deduce? I can deduce that AE, that's the vertices in positions 1 and 2, is identical to CE, and DE, that's positions 3 and 2, is identical to BE. And therefore we have proved that E is not only the midpoint of AC, but it's also the midpoint of BD. So therefore, if we have a parallelogram, we can say that the diagonals bisect each other. We now consider the converse theorems. In other words, which ways do we have to prove that a quadrilateral is a parallelogram? Now here I've summarized all the properties that we've proved. So if we want to prove that a quadrilateral is a parallelogram, it can be proved in any of the following 5 ways. If you can prove that pairs of opposite sides are parallel, then it will be a parallelogram according to the definition. If you can prove that both pairs of opposite sides are equal, then according to our theorem 1, it will be a parallelogram. If we can prove that both pairs of opposite angles are equal, then it will also be a parallelogram. If you can prove that diagonals bisect each other, right, then it will also be a parallelogram. And the last one, if we have one pair of opposite sides equal as well as parallel, then we can also prove, right, that it will be a parallelogram. We have not specifically proved this one, but it is relatively easy to see that. For instance, if we know that AD is equal to BC in length, and we know that AD is parallel to BC, right, then we're saying we can easily prove that AB will also be parallel to DC, and which will make it a parallelogram. We will have a look at this at a later stage. Now prove that if pairs of opposite sides are equal, then we can prove that the quadrilateral is a parallelogram. So given a quadrilateral with pairs of opposite sides equal, therefore we know that AD is equal to BC and AB is equal to CD. We need to prove that ABCD is a parallelogram, and this we can do by proving that pairs of opposite sides are parallel. The construction here is to draw diagonal indicated by the line segment AC. If we compare the two triangles here, namely triangle ADC with triangle ABC, then it's pretty clear that 3 sides of the one triangle is equal to 3 sides of the second triangle, because we were given that AD is equal to CB or BC, AB equal to CD, and AC common. So therefore the two triangles, again make sure of the correct order, the triangle ADC is congruent to the triangle CBA due to the side congruency. What can we conclude now? Firstly, we can conclude that line segment AD must be parallel to line segment BC, because alternate angles DAC and ACB or BCA must be equal. In a similar way, line segment AB will be parallel to line segment DC, because alternate angles BAC and DCA are equal. So therefore we have proved that two pairs of opposite sides, or both pairs rather of opposite sides, are parallel, and therefore from the definition we know that ABCD must be a parallelogram. We now prove the theorem that if pairs of opposite angles are equal, then the quadrilateral is a parallelogram. So we are given a quadrilateral ABCD with the opposite angles A and C equal, as well as the opposite angles B and D equal. We want to prove that this quadrilateral is a parallelogram, and we will prove it if we can show that line segment AD is parallel to line segment BC, and that line segment AB is parallel to line segment CD. Now let's start off with what we know. We have proved it earlier, that the sum of the interior angles of any quadrilateral is 360 degrees. So if we add the 4 angles, we will get that the sum is 360 degrees. But angle A is equal to angle C, so I can replace angle C also by A. So I get A plus A, or twice A, and angle B is equal to angle D, so I can replace angle D also by angle B. So we get twice angle A but plus twice angle B is 360, or in other words, angle A plus angle B is 180. But angle A and B are co-interior angles. So therefore we know that the sum of the co-interior angles is 180 degrees, and this implies that line segment AD must be parallel to line segment BC. In a similar way, we can show that angle A plus angle D is also equal to 180 degrees, but angle A and D are again co-interior angles with reference to the transversal AD. So this simply then means that the sum of two co-interior angles is equal to 180. Therefore line segment AB must be parallel to line segment CD, and therefore we have proved that both pairs of opposite sides are parallel, and therefore ABCD must be a parallelogram. We would like to prove that if the diagonals in a quadrilateral bisect each other, then this quadrilateral is a parallelogram. Now consider this particular quadrilateral ABCD, and the only thing we know is that AE is equal to CE. In other words, E is the midpoint of diagonal AC, and BE equals to DE. So therefore diagonals bisect each other. We want to prove that this quadrilateral is a parallelogram. And we can achieve this if we can prove that line segment AD is parallel to line segment BC, as well as showing that line segment AB is parallel to line segment DC. So firstly, we compare the two red triangles. You can check the names here. I'm just going to refer to the color and the numbers. So what do we know? We know that in the top red triangle, AE is equal to CE in the bottom red triangle. In the same way, DE is equal to BE, that's given. And angles 1 and 2 are vertically opposite. So therefore, two sides and the included angle of the one triangle is equal to two sides and included angle of the other one. So therefore, the two triangles are obviously congruent. What can we conclude from this? We can conclude from this that angle 5 must be equal to angle 6. Now angle 5, another name for that, will be angle DAC, and angle 6 will be BCA. Now 5 and 6 are actually alternate angles if we consider the line segments AD and BC and we take AC as the transversal. So therefore we know that alternate angles are equal, and for that reason we can conclude that AD is parallel to BC. In a similar way, by comparing the two blue triangles, we can show that line segment AB is parallel to line segment DC. So let's just look at this pretty quickly. We can show that the two blue triangles are congruent. Let's see why. We know that AE is the same as CE, and we know that BE is the same as DE, and 3 and 4, angles 3 and 4 are vertically opposite. So therefore the two blue triangles are congruent, and therefore we can conclude that angle 7 and 8 must be equal. Note that angle 8 we can write as angle ABD, and angle 7 as angle CBD. But these angles, namely angle 7 and 8, are alternate angles if we consider the line segments AB and DC and the transversal BD. So therefore again we have two alternate angles equal, and therefore the two line segments AB and DC must be parallel. So what do we have? We have therefore that both pairs of opposite sides in this quadrilateral are parallel, and therefore ABCD must be a parallelogram. In this theorem we would like to prove that if one pair of opposite sides in a quadrilateral is equal and parallel, then the quadrilateral is a parallelogram. So we have the following. We have a quadrilateral ABCD, and we know two things. We know that AD is equal to BC, and furthermore that AD is parallel to BC. If we want to show that this quadrilateral is a parallelogram, we only need to prove that line segment AB is also parallel to line segment DC, because then according to the definition the quadrilateral will be a parallelogram. Now to achieve this, we compare the red and the blue triangles, namely triangle ADC and triangle CBA. And what do we know? Well, it's given to us that AD in the red one is equal to BC in the blue one. Furthermore, line segment AC, or AC is common, it belongs to both. Furthermore, angle 1 will be equal to angle 2. It's actually alternate angles because we know that AD is parallel to BC with AC as a transversal. Now because we now have two sides and an included angle of the red triangle equal to two sides and the included angle of the blue one, we can conclude that the two triangles must be congruent. And from this we can then deduce that angle 3 must be equal to angle 4. Now remember, angle 3 is really angle CAB, and angle 4 is angle ACD. So these two angles are alternate angles and they equal, and therefore the two line segments AB and DC must be parallel, because AC serves here as a transversal. So what do we have now? We have now that both pairs of opposite sides are parallel, and therefore ABCD must be a parallelogram. Let us look at example 1 where we apply the parallelogram properties. We are given a parallelogram ABCD. In other words, we know that pairs of opposite sides must be parallel. Furthermore, AE is drawn with D an element of AE, or we could also say AD is produced to the point E. Furthermore, it is given that angle CDE is 4 times angle B. You are requested to calculate the measures of angles A and B. Now firstly, angle C here is alternate to angle CDE, and therefore, because angle CDE is 4B, we can say that angle C is equal to 4 times angle B. But angle B plus angle C being co-interior angles, and of course we know that AB is parallel to CD, so the sum of these two co-interior angles must be 180 degrees. So if we replace angle C by 4 times angle B, then we get 5 times angle B is 180 degrees of angle, or angle B is equal to 36 degrees. Furthermore, it is also known that the sum of angles A and B is 180 degrees, being co-interior angles, and it is known that AD is parallel to BC. Therefore, angle A is 180 degrees minus angle B, or 180 degrees minus 36 degrees from our calculation. Therefore, angle A turns out to be 144 degrees. We consider a second example where we apply the properties of parallelograms. We are given triangle ABC with D and E the midpoints of AB and AC respectively, and then furthermore it is given that line segment CF is parallel to line segment BA with F on DE produced. So firstly you got to prove that triangle ADE, this little one here at the top, is congruent to this little triangle here at the bottom right, namely triangle CFE. Then after that we need to show that quadrilateral DBCF is a parallelogram, and then show that DE is equal to half of BC, and furthermore that line segment CD bisects line segment BF. Now to prove the first part, namely that these two triangles are congruent, we start off by saying that angle DAE is equal to angle FCE, because they alternate angles, and they are equal because they not only alternate angles, but because a line segment AB is parallel to line segment CF, they will be alternately equal to each other. Furthermore, angle AED is equal to angle CEF because they're vertically opposite, and furthermore it's given that AE is equal to CE. So therefore the two triangles will be congruent because two angles and a side and each one are actually equal. So that proves the first part. Then we need to show that DBCF is a parallelogram. Now, what do we know already? We already know that DB is parallel to CE. So if we could still show, in addition, show that that DB is equal to CF, then we will have that a pair of opposite sides are not only parallel but also equal, and then from a previous converse theorem this will be a parallelogram. So all we really need to do is try and show that BD is equal to CF. So I start with BD, and BD is obviously equal to DA because we know that D is the midpoint of AB. But we've proved, due to the congruency, that DA or AD is the same as CF or FC from the congruency. So therefore we've seen that now that BD is equal to CF. So therefore we have proved what we want to do, because in addition it was given that BD is parallel to CF. So therefore BDCF is a parallelogram for the simple reason that opposite sides are not only parallel but also equal to each other. Thirdly, we need to show that DE is half of BC. Now, firstly, DE is half of DF, simply because DE is equal to EF from the two congruent triangles. So in other words, E is really the midpoint of DF, but DF in turn is equal to BC because the opposite sides of a parallelogram must be equal, and that then proves this third part. And finally, the last part, which is pretty straightforward, they ask us to prove that line segment CD and line segment BF bisect each other. Now they are the diagonals of parallelogram DBCF, and because the diagonals of a parallelogram bisect each other, this proof will then be concluded. You should now be in a position to tackle tutorial 1 dealing with parallelograms. In the first problem, we are given that M and N are 2 points on AD and BC respectively of parallelogram ABCD. So we know that ABCD is a parallelogram. In other words, the two pairs of opposite sides must be parallel. Now M and N are 2 points such that AM must be equal to NC. Now the request is to prove that this shaded quadrilateral here, BMDN, is a parallelogram. In the second problem, they say that K and T are the midpoints of line segments AD and BC respectively of parallelogram ABCD. So in other words, we also know that ABCD is a parallelogram, therefore pairs of opposite sides must be parallel. Then you need to prove that BD and KT bisect each other. In the third problem, Here again we have a parallelogram ABCD, in other words opposite sides must be parallel. M and N are points on the diagonal AC such that AN is equal to MC. So now you got to prove firstly that triangle ABN is congruent to triangle CDM, that NBMD is a parallelogram, and furthermore that BD bisects MN. I suggest that you pause the video, do tutorial 1, and then come back and view possible solutions. Let us look at the suggested solution to problem 1 of tutorial 1. You need to prove that BMDN is a parallelogram. Now what we already know, we know that AD is parallel to BC. In other words, MD is also parallel to BN. So if we can only prove that MD is equal to BN, then we will have that a pair of opposite sides is parallel and equal, and then it will be a parallelogram. And this is exactly what we're going to do. We know that AD is equal to BC because they're opposite sides of a parallelogram. So if I take AD and I subtract from that AM, then it will be equal to BC subtracting NC from that, because remember we subtract two equal segments from each one. Now AD minus AM is really MD, and BC minus NC is BN. So therefore we have proved that for the shaded parallelogram the pair of opposite sides are equal, but we already know that they parallel. Therefore we can conclude that this quadrilateral is a parallelogram because opposite sides are equal and parallel. Let us consider a suggested solution to problem 2. We need to show that in this shaded quadrilateral that diagonal BD bisect diagonal KT. Now that will be the case if BKDT is a parallelogram. So really all we need to do is to show that BKDT is a parallelogram. And there we already know that AD is parallel to BC. In other words, therefore KD will also be parallel to BT. So we only need to prove in addition that KD is also equal to BT. Now that's what we will do here. We know that AD is equal to BC. They are the opposite sides of a parallelogram. But we know that K and T are the midpoints of AD and BC respectively. So if I take half of AD, I can either have AK or KD, and if I take half of BC, I can either say I got BT or TC. So half of AD, we describe that as KD, and half of BC, we describe that as BT. So therefore we've proved that KD is equal to BD. But line segment KD is parallel to line segment BT for the simple reason that it is a portion of two parallel line segments AD and BC. Therefore KBTD, the shaded quadrilateral, is a parallelogram because opposite sides are not only equal but they also parallel, and therefore the two diagonals BD and KT bisect each other, because this is what happens if we have a parallelogram, like in the case of parallelogram KBTD. We know that the diagonals of the parallelogram must bisect each other. We now look at the suggested solution to problem 3 of tutorial 1. we are given this particular quadrilateral, knowing that it's a parallelogram, and further knowing that AN is equal to CM. Firstly, we need to prove that that triangle ABN is congruent to triangle CDM. Now, what do we know? We know that AN is given equals to CM. Furthermore, we know that AB is equal to CD or DC, being the opposite sides of parallelogram ABCD, and it's given that ABCD is a parallelogram. Furthermore, we can see that angle 1 is equal to angle 2 because they are alternate angles, and because we know that AB is parallel to CD, and if we take AC as a transversal, then it's obviously that 1 is alternately equal to angle 2, or more specifically angle BAN is alternately equal to angle DCM. Therefore, we've proved that two sides and an enclosed angle of the one triangle is equal to two sides and enclosed angle of the second triangle, and therefore the two triangles will be congruent, the reason being S angle S. Next, we need to show that the blue shaded quadrilateral is a parallelogram. Now, what do we know? We already know from the congruency of these two triangles that BN is the same as DM. So we know that two opposite sides are equal. So all we need to do is to prove that they are actually parallel as well. From the congruency, we know that angle 3 is equal to angle 4. But if we should consider the line segments BN and MD and the transversal ANMC, then 3 and 4 are not only equal, but they exterior alternate angles. And because exterior alternate angles are equal, we can then conclude that BN must be parallel to DM. So what have we showed then? We've showed that two opposite sides are not only equal but also parallel. Therefore, NBMD is a parallelogram. Lastly, we need to show that why does BD bisect NM. Now that's plain and simple, because we've proved that this blue quadrilateral is a parallelogram and the diagonals of a parallelogram bisect each other. Therefore, line segment BD and line segment NM, being the diagonals of this particular parallelogram, must bisect each other. In lesson 2, we look at the classification of quadrilaterals. The outcomes for lesson 2. In this lesson, we will focus on the definitions of different types of quadrilaterals, the properties of different quadrilaterals, the areas of different quadrilaterals, the relationships between quadrilaterals, and disprove conjectures by means of a counterexample. Next, we look at the definitions of different quadrilaterals and the connections between the various quadrilaterals. We start off with a normal quadrilateral, which is simply a four-sided polygon. Then we define the trapezium, and the definition of the trapezium say it is a quadrilateral with one pair of opposite sides parallel. So this is exactly what a trapezium is. And therefore you can see that a trapezium will always be a quadrilateral, but a quadrilateral will not always be a trapezium. Next we move on to a kite. In the kite's definition we say two pairs of adjacent sides must be equal. Adjacent we can also use the word consecutive You see, this in a quadrilateral, there is actually 4 pairs of adjacent or consecutive sides. No, you can check that. But the definitions say that 2 pairs of adjacent sides must be equal. So there's the first pair and there is the next pair. But can you see this pair and this one is not necessarily equal. So therefore, a kite is definitely a quadrilateral, but a kite is not a trapezium. Or a quadrilateral is not always a kite. And then we move on to the parallelogram, which we defined already as a quadrilateral with 2 pairs of opposite sides parallel. That means that a parallelogram will be a trapezium, and of course also it will be a quadrilateral. The next definition is a rectangle. Now what we do to get to a rectangle is we simply say it must be a parallelogram and one of the angles must be 90 degrees. Obviously the implication will be that if one of the angles is 90 degrees, all 4 the angles will be 90 degrees. So therefore a rectangle will always be a parallelogram, a rectangle will always be a trapezium, and it will always be a quadrilateral if you follow this particular route. Then we move on to the rhombus. Now a rhombus is defined as a parallelogram with 2 adjacent sides equal, right, or 2 consecutive sides equal. Let's assume this side is equal to that one. Obviously then we can prove, because it's a parallelogram, that all the sides must be equal. So therefore a rhombus is clearly a parallelogram. But a parallelogram is not always a rhombus. A rhombus is always a kite. Right, because there is at least 2 pairs of adjacent sides that will be equal. And finally we have the quadrilateral, the square, which is a parallelogram, and one of the angles must be a right angle. So in other words, it's really a rectangle, but then furthermore 2 adjacent sides must be equal. So something like this. So therefore a square is a rectangle and therefore also a parallelogram, but a square is also a rhombus. You see, the square is the ultimate quadrilateral, because a square is a rectangle, is a parallelogram, is a trapezium, and is a quadrilateral. Or we can go this route, we can say the square is a rhombus, is a kite, or we can say a square is a rhombus and therefore a parallelogram. Go different routes, but we can go this route too and say a square is a rhombus, it's also a kite, and it's also a quadrilateral. So this is a very important diagram, and you need to understand the definitions and the connections. We now look at the properties of a kite. Now in this particular sketch we have summarized all the properties of a kite. Now remember, according to the definition, a quadrilateral is a kite if 2 pairs of adjacent sides are equal. In other words, side AB is equal to side BC and they adjacent, and side AD is equal to side CD. They also adjacent. But note, AB is not necessarily equal. Right? There can be situations, but they also a pair of adjacent sides. Furthermore, what can we say? The diagonals cut each other perpendicular. So this angle is 90 degrees. Of course, these are properties that we still need to prove. Right. The only thing that we know now is the definition. Furthermore, there is what we talk about, the long diagonal and the short diagonal. So what does the long diagonal do? The long diagonal bisects the shorter diagonal. Right. So if we consider that particular point of intersection, these two pieces must be equal in length. The long diagonal also bisect the opposite angles, so the two angles here will be equal and the two angles here at the bottom, and it also bisects the area of the kite. So the area of triangle BAD will be the same as BCD, which really means that these two triangles will be congruent. I can see a lot of congruent triangles, even this two here and this two here at the bottom will be congruent. Now this is simply the properties of the kite. We can only accept the definition at this stage. The other properties still need to be proved. Let us consider the properties of a rectangle. Now here is a rectangle. I've tried to summarize all the properties of the rectangle in the sketch. Now of course the definitions say that it must be a parallelogram, so therefore it must have all the properties of a parallelogram. So in other words, pairs of opposite sides are not only equal but also parallel. Diagonals must bisect each other, but in addition we know that the one angle is 90 degrees, and therefore we can, because of the fact that for instance D and B are co-interior angles, B must be equal to 90 degrees, and because C and D are also co-interior angles, because AC is parallel to DB, C must be 90, and then clearly A must be 90 degrees. But there is a new property here which we need to prove, which doesn't come directly from the properties of a parallelogram, and this is that the diagonals of a rectangle must have the same length. In other words, AD must be equal to CB in length, and therefore if we assume the property of a parallelogram that diagonals bisect each other, then you can see all four these pieces must have the same length. So we need to prove this, and in order to prove this we consider triangle ABC, which we know is a right angle triangle, and triangle BAD, which is also a right angle triangle. So firstly we know that angle A is equal to angle B, and they both 90 degrees because they are co-interior angles, and because AC is parallel to DB, their sum must be 180, therefore both of them must be equal to 90 degrees. Furthermore, AB is a common side, and AC is equal to DB. They are the opposite sides of a parallelogram, so therefore the two triangles must be congruent, because two sides an enclosed angle of the one is equal to two sides an enclosed angle of the other one, and therefore we can conclude that BC must be equal to AD. We look now at the properties of a rhombus. Now if we summarize all the properties of a rhombus, this is what we will get. Some of them we will know at this stage, some still need to be proved. Firstly, the rhombus must have all the properties of a parallelogram, and in addition two consecutive sides must be equal. So let's see what we know. Therefore we know that AC is equal to CD according to the definition, but CD is equal to AB and AC is equal to DB according to the properties of a parallelogram. So all the sides must have the same length. Furthermore, opposite sides will not only be equal but also be parallel. Angle C must be equal to angle B. Angle A must be equal to angle D. But you can see I've indicated some additional stuff there. We also know that from the properties of a parallelogram, diagonals must bisect each other. So that's nothing new. But there's two more things we need to prove. That the diagonals not only bisect each other, but bisect each other at right angles. So we need to prove that this angle is 90 degrees and that it also bisects the opposite angles. So in other words, that all these angles here, 4 angles, can be indicated by a black dot, because we know angle C is equal to angle B, so therefore half of angle C must be equal to half of angle B, and if they bisect each other, then of course right, they must be equal. And the same will apply for angles A and D. So how do we prove it? We know that ABCD is a parallelogram and the diagonals bisect each other. So what we do is we compare these two triangles, namely triangle AEC, we compare it with triangle DEC, and what do we have? We have that the two adjacent sides are equal in length according to the definition of a rhombus. We know that AE is equal to DE because the diagonals of a parallelogram must bisect each other, and CE is common. So therefore the two triangles will be congruent because 3 sides of the one is equal to 3 sides of the other one. Now what can we conclude from that? We can conclude that angle AEC must be equal to angle DEC in measure, but together they form a straight angle. Angle AED is a straight angle. Now if they equal, then each one of them must be equal to 90 degrees. So that then proves the first part, that the diagonals bisect each other at right angles. Furthermore, we know that angle ACE is equal to angle DCE from this congruency. Furthermore, angle DCB is alternately equal to angle CBA. So this can also be indicated with a black dot. And furthermore, angle ACB is alternately equal to DBC, so it can also be indicated by a black dot. So all 4 these angles are equal, so therefore diagonal CB also bisects opposite angles C and B. In a similar way, we can prove that AD bisects angles D and A. All you need to do is you can in a similar way show that triangle CDE is congruent to triangle BDE, and therefore these two angles which is indicated by 2 unshaded dots must be equal in length, and this top dot is alternately equal to this angle EAB, and this bottom one alternately equal to that one. So again, all 4 these little angles can be indicated by an unshaded dot, which then proves this particular property. In this particular sketch, we've summarized all the properties of a square. Now, a square must have all the properties of a rectangle, all the properties of a rhombus, all the properties of a parallelogram, and all the properties of a kite. So let's summarize it. We know it's a rectangle with 2 adjacent or 2 consecutive sides equal, so clearly all 4 the sides must have equal length. All 4 the angles must be equal to 90 degrees because it's a rectangle. The diagonals must be equal in length because it's a rectangle. The diagonals must bisect each other at right angles because it's a rhombus, and it must bisect all the opposite angles because it's a rhombus. Can you see all these pieces, or that particular point there being the midpoint of DB and AD? It means that all these little pieces will have the same exactly the same length. Let us compare some sets of quadrilaterals. Firstly, we see that if a quadrilateral is a square, then it will be a subset of the set of rectangles, and it will be a subset of the parallelograms. And of course, the rectangle will always be a parallelogram. Considering this one, we know that a square is always a parallelogram, a rhombus, and a rectangle is always a parallelogram. A square is always a rhombus because this particular intersection is a subset of the rhombuses, and a square is always a rectangle. But a rectangle is not necessarily a rhombus, and nor is a rhombus necessarily a rectangle. So we can make a couple of conclusions here that all squares are proper subsets of the rectangles, and all rectangles are proper subsets of a parallelogram, and all squares are proper subsets of the parallelograms. So all squares, furthermore, if we look at this sketch, is always a rhombus, all squares are always a parallelogram, and all rhombuses are always a parallelogram. If we look further here, then a rhombus is not always a rectangle, and a rectangle is not always a rhombus. That should be pretty clear. We can use the counterexample method to disprove conjectures. We can make certain conjectures, like for instance this one. If a quadrilateral is a rhombus, then it will be a rectangle. We can find in this case a counterexample. Now here is an example of a rhombus. The question is, will it be a rectangle? And of course this is not necessarily a rectangle, because we're not sure whether any of these interior angles A, B, C or D is 90 degrees. So this polygon is a rhombus but not a rectangle. Therefore the conjecture is disproved and thus invalid, because we can find an example of a rhombus which is not a rectangle. Note that numerous specific examples supporting a conjecture do not constitute a general proof. For example, we can find many examples to support the following conjecture. If a quadrilateral is a square, then it will be a rhombus. The validity of this conjecture or any other conjecture can only be confirmed by means of a formal proof, and not by finding a lot of examples where it's working. Such a type of thing is simply an investigation which is pointing towards a particular conjecture, but the validity of that will only be established by means of a formal proof. We are now ready to look at tutorial 2, where the focus is on the classification of quadrilaterals. First question, or first problem, is where we ask, is every rectangle a parallelogram? And secondly, we ask the question, is every parallelogram a rectangle? You must give or state reasons for your answers. In the second problem, PQRS is a quadrilateral having PQ equals to QR equals to RS equals to SP, and angle P is 90 degrees. You need to prove that PQRS is a square. In the third problem, the diagonals AC and BD of parallelogram ABCD bisect each other at right angles. You need to prove that ABCD is a rhombus. The fourth question or problem, if angle A and C of parallelogram ABCD are bisected by line segment AC, prove that ABCD is a rhombus. And finally, if we assume that K represent the set of kites, R the set of rectangles, and S the set of squares, you must state with a reason or reasons whether the following statements are true or false, and also correct false statements. Firstly, is S a subset of R? In other words, is every square a rectangle? Is K a subset of R? Is S a subset of R, S a subset of K, and R a subset of K? I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us look at the suggested solution to problem 1 of tutorial 2. Now, this particular problem deals with the relationship between rectangles and parallelograms. And if we consider this diagram, then we'll see that the set of rectangles is a subset of the set of parallelograms. In other words, every rectangle is a parallelogram, but every parallelogram is not a rectangle. So every rectangle is a parallelogram. First question was, is every rectangle a parallelogram? So the answer to that is yes. Second question, is every parallelogram a rectangle? And the answer to that is no. Because we can find a counter example. Every parallelogram is not a rectangle. So if I take this one for instance, then this parallelogram is not necessarily a rectangle because we do not know whether there is an angle of 90 degrees. While if we have a rectangle, we do know that opposite sides will be parallel and therefore it will be a parallelogram. So rectangles is therefore a subset of parallelograms, but parallelograms is not a subset of rectangles. You know, in a rectangle, pairs of opposite sides are parallel, therefore it fits the definition of a parallelogram. While in a parallelogram, one of the interior angles is not necessarily 90 degrees, therefore the parallelogram definition is weaker than the rectangle definition. We need to add the additional condition that one of the angles must be 90 degrees before a parallelogram can be classified as a rectangle. Let us look at the suggested solution to the second problem of tutorial 2. Here we are given a quadrilateral PQRS with all four the sides equal to each other and angle P equals to 90 degrees. We need to prove that PQRS is a square. Now remember, PQRS will be a square if we can prove that it's a rectangle, because a square is defined as a rectangle with one of the angles 90 degrees. And to prove that PQRS is a rectangle, we really need to prove that PQRS is a parallelogram, because if PQRS is a parallelogram and we know that one of the angles is given to be 90 degrees, then according to the definition of a rectangle, it will be a rectangle. So what do? We consider these two triangles, and what do we know? We know that QP is equal to SR, that's given. PS is equal to QR, given, and QS is common. Therefore the two triangles must be congruent, because three sides of the one is equal to three sides of the other one. So therefore we can then say that PS, line segment PS, must be parallel to line segment QR, because angle PSQ is alternately equal to angle RQS from the congruency. And in a similar way, PQ is parallel to SR, because angle PQS is alternately equal to RSQ. Now, if we prove that two pairs of opposite sides are parallel, then it means that this quadrilateral is a parallelogram which contains a right angle, and therefore it must be a rectangle. And because it's a rectangle, we have therefore proved that PQRS will be a square, because we said right in the beginning, all we need to do is to prove that PQRS is a rectangle, because then it will be a square. Let us look at the suggested solution to problem 3 from tutorial 2. Well, the diagonals AC and BD of a parallelogram is given bisect each other at right angles. So we know that this is 90 degrees. Of course, we know that ABCD is a parallelogram, so therefore all the properties for the parallelogram will be applicable. We need to prove that ABCD is a rhombus. Now, according to the definition of a rhombus is a parallelogram where two adjacent sides or consecutive sides are equal. We already know it's a parallelogram, so all we need to do to prove that this quadrilateral is a rhombus is to prove that two consecutive sides must be equal. So it will be sufficient if we can prove that AB is equal to AD. And to do that, we compare triangle AOB with triangle AOD. And firstly, we can see that BO must be equal to DO, because remember it's a parallelogram and therefore the diagonals bisect each other. AO is common. This angle is given to be 90 degrees, therefore angle AOD must also be equal to 90 degrees, because BOD is a straight angle. So therefore the two little triangles will be congruent, because two sides and the enclosed angle of the one is equal to two corresponding sides and enclosed angle. And therefore we can conclude from this congruency that AB must be equal to AD, which then proves that this quadrilateral is a rhombus. A suggested solution to problem 4 of tutorial 2 will be the following. We are given a parallelogram ABCD, and it's also given that the diagonal AC bisect angles A and C. We must prove that ABCD is a rhombus. Now remember, ABCD will be a rhombus if it's a parallelogram, and that we know, and two consecutive sides equal, and that we still don't know. So all we really need to show is that two consecutive sides will be equal, or more specifically, if we can prove that AB is equal to BC, then ABCD will be a rhombus. Now we know that angle A is equal to angle C, because they are opposite angles of a parallelogram. So half of angle A must be equal to half of angle C, but half of angle C can be written as angle BAC, and half of angle C can be written as BCA, because we were given that AC bisect angles A and C. So therefore that means that triangle ABC is an isosceles triangle, and therefore AB must be equal to BC, because the base angles have been proved to be equal. And this then concludes the proof, because now we've showed that AB is equal to BC, in other words two consecutive sides are equal, therefore this quadrilateral will be a rhombus. In problem 5 of tutorial 2, we're given a couple of statements. We need to find out whether the statements are true or false, and if they're false, we had to correct them. Well, it deals with the relationship between kites, rectangles, and squares. And this is how we can sketch it. Every square is a kite, every square is a rectangle, but not all rectangles are kites. It's only those rectangles that's squares that are actually kites, and it's only the kites that are squares that's also rectangles. So there's certain kites that is not a square, there's certain kites that's not a rectangle, and the same way there's certain rectangles which is not a square as well. So if we take all these statements, just give some examples there. The first statement, all squares are also rectangles. That's obvious, right? Because if you have a square, then we know it's a rectangle, because it's a parallelogram with one of the angles equal to 90 degrees. So therefore the set of squares is a subset of the set of rectangles. What about 5.2? The set of all kites is a subset of the set of rectangles. This is false, because not every kite is a rectangle. Because we can find a counter example. This is a kite, and it's definitely not a rectangle, because there's no ways that we can say that it's a parallelogram with one of the angles 90 degrees. So we need to correct the statement, and we can correct it by saying that the set of kites are not a subset of the set of rectangles. The last statement has been made here, that the kites, all kites are a subset of the set of squares, which is also false, because if you look at this particular kite, then it's clearly not a square. But what is true is that the set of all squares is a subset of the set of all kites. We now consider the area formulas for the quadrilateral, the kite, and the trapezium. Now, if we have a quadrilateral, then of course we can subdivide it into two triangles, each with their own base and height as indicated. So the area of the quadrilateral is simply the sum of the two areas of the two triangles. Remember, the area of a triangle is half base times height, so the blue one is half AD times small h, and the other one is half BD times capital H, and if you put it together, this will be the formula. If we look at a kite, what can we say? If we utilize this quadrilaterals formula, then we can say the area of this kite is the area of the blue triangle, which is half base, half AC times small h, plus half AC times capital H. And now AC can be taken out as a common factor, and then we multiply with the sum of the two heights, and small h plus capital H is equal to BD. Right, so therefore AC and BD are the diagonals, so the area is half the product of the diagonals. If we come to the trapezium, remember here we have a pair of opposite sides parallel. Again, we split it up in two triangles. Note, because this angle D is obtuse, I need to drop a perpendicular to CD produced to get the height of the red triangle. So clearly the area of a trapezium is the area of the blue one, which is half the base AB times H, while the area of the red one is half the base, which in this case is CD, and the height is the same. You know, the distance between two parallel lines remains constant. So now we can take a half h out as a common factor, and we get AD plus CD. And AB plus CD is simply the sum of the two parallel sides. So therefore, in words or verbal form, the area of a trapezium is half multiplied by the distance between the two parallel sides, that's h, multiplied by the sum of the two parallel sides. We also look at the areas for the parallelogram, rectangle, rhombus and square. Consider a parallelogram here where small h is the distance between the two parallel sides AB and DC, while capital H is the distance, shortest distance between the parallel sides AD and BC. So we can again, as before, say that the area of a parallelogram is simply the sum of the areas of the two triangles. So of the red one, it's half AB times H, and the blue one is half DC times H. So if we can take half H out as a common factor, we get AB plus DC, but don't forget that AB and DC have the same length. So I can either replace DC by AB or AB by DC, so I get twice AB. So the 2's cancel out, so you just get H times AB. So base times height, but we can also consider the base to be AD, and then the height will be the capital H. So in general, the area of a parallelogram is base times height. If we look at a rhombus, now remember, this is the properties of a rhombus, so again we can say that the area of the rhombus is half AC times DE, because remember, we know that the diagonals bisect each other perpendicular. So that is the red triangle's area. In a similar way, the area of the blue one is half the base AC times the height, which is EB. So we can take half AC out as a common factor, and we get DE plus EB, but DE plus EB is the diagonal DB, so we get half the product of the diagonals. If we come to the rectangle, I think we're all familiar with this. If you should subdivide this into two triangles, then both these triangles will be right angle triangles. Each will have an area of half B times H, so the area is plain and simple base times height, which you can also deduce from the area of the parallelogram, because this is a parallelogram. And then we look at the square, and the square is also a parallelogram. The side lengths are all the same, so it's base times height, so it's L times L. So the area of a square is simply the square of the length of one of the sides. We can now look at tutorial 3, dealing with the areas of quadrilaterals. In the first one, you need to calculate the area of a rhombus having diagonals x plus 3 and 2 times x minus 3 units of length, obviously in terms of x. In the second one, you have a quadrilateral ABCD. Area of triangle ADC is given, and the heights of triangles ADC and ABC are also given. So now we must find the area of a quadrilateral. Obviously it will be good to make a sketch and put all the details within the sketch. In question number 3, the area of a rhombus is given and one of the diagonals is given. You need to calculate the length of AC as well as find the area of triangle AOD if O is the point of intersection of the diagonals. And in the fourth problem, it's given that ABCD is a parallelogram having AD equals to 120 millimeters and BC 50 millimeters, and a line segment AD parallel to line segment BC, and the area of triangle ABD has 48 square centimeters. You need to calculate the perpendicular distance between the two parallel lines as well as the area of the trapezium. I suggest that you pause the video, do tutorial 3, and then come back and view possible solutions. A suggested solution to problem 1 of tutorial 3 can be the following. You need to calculate the area of a rhombus, and the diagonals are given in terms of x. So we know that the area of a rhombus is half the product of the diagonals, so it's half AD times CB, but AD we can assume is 2 times x minus 3, and then of course CB must be x minus 3, the 2's cancels out, and we get a simple expression here in terms of x squared minus 9 square units. Let us look at a suggested solution to problem 2 from tutorial 3. We are given a quadrilateral ABCD. We also know the area of the red triangle to be 24 square centimeters, and it's also given that the heights of the red and the blue triangle are 60 millimeters and 70 millimeters respectively, or 6 centimeters and 7 centimeters respectively. So firstly, what we can do, if we start with the red triangle, we know its area, and we can say that its area is half the base AC times the height DE, and because we know DE and we know the area, we can calculate AC to be 8 centimeters. Once we know the base AC, which also forms the base for the blue one, we can proceed to calculate the area of triangle ACB as half the base AC times the height FB, and that we get is 28 square centimeters. And of course, to find the area of the quadrilateral, we simply add the two areas of the two triangles, namely 24 and 28 square centimeters, or 52 square centimeters. Let us look at a suggested solution to problem 3 from tutorial 3. We are dealing here with a rhombus. We know the area of the rhombus. We know one of the diagonals BD. They ask us to calculate the second diagonal AC, and we need to find the area of triangle AOD, where O is the point of intersection of the diagonals. Now we know that the area of a rhombus is half the product of the diagonals, which is half AC times BD. We know the area of the rhombus, we know BD, so therefore we can calculate AC, and we see that that is 20 centimeters. Now to find the area of the smaller triangle AOD, we make a couple of observations. We know that this is a right angle triangle, so we can easily find the area if we know what is AO and OD. But AO is half of AC, so that's 10 centimeters, and OD is half of BD, which is half of 10, and that's 5 centimeters. So therefore the area of triangle AOD is half AO times OD, so it's half 10 times 5, or 25 square centimeters. Just a bit of a reflection. Actually, it's easy to see that all four of these triangles will have exactly the same area, so each of them will have an area which is a quarter of the rhombus, or 25 square centimeters. We now look at a suggested solution to problem 4 of tutorial 3. Here we have a trapezium, and it's given that AD is 120 millimeter or 12 centimeters, BC 5 centimeters or 5 millimeters, and that AD is parallel to CB. They also tell us that the area of triangle ABD is 48 square centimeters. So firstly we need to find the perpendicular distance between the two parallel sides, and finally the area of the trapezium. So if we start off with a shaded triangle, we know that the area of that is half base AD times the height, and we know the area of that as well as we know the value of AD, so we can calculate the perpendicular distance between the two parallel sides to be 8 centimeters. And once we know that, we can then calculate the area of the trapezium, because we know it's half multiplied by the distance between the two parallel sides multiplied by the sum of the two parallel sides, and H as well as AD and BC all are known to us. So if we calculate this, we find that the area of the trapezium is 68 square centimeters. In lesson 3 we focus on the midpoint theorem. Let us look at the outcomes for lesson 3. In this lesson we will prove the following results. Firstly, the line segment joining the midpoints of two sides of a triangle is parallel to the third side, and its length is equal to half that of the third side. This is known as the midpoint theorem. And then we will also prove that the line segment drawn through the midpoint of one side of a triangle parallel to the other side bisect the third side. And that we will also prove that if three or more parallel lines make equal intercepts on a given transversal, they will make equal intercepts on any other transversal. And then we will consider deductions and applications of the midpoint theorem. Let us look at the proof of the midpoint theorem. We are given a triangle ABC with D and E, the midpoints of AB and AC respectively. It is expected of us to prove, so it's required to prove that firstly that line segment DE is parallel to line segment BC, and that DE is half of BC. Now in order to prove this, we do the following construction. We draw DE and produce it to F, so that DE is equal to EF. And then addition, we draw line segments CF, AF and DC. Now let us look at the proof. Firstly, we observed that ADCF, this quadrilateral, is a parallelogram because it's clear here that the diagonals bisect each other. So from this we can therefore conclude that opposite sides must be equal and parallel. So therefore CF is equal to AD, and furthermore line segment CF is parallel to line segment AD. But CF is equal to BD. What is the reason behind that? Because AD is equal to BD, D being the midpoint of AB. So really I proceed from there, from AD, and I say that AD is equal to BD because AD is equal to BD because D is the midpoint of AB. Well, instead of saying line segment CF is parallel to line segment AD, I could say that line segment CF is parallel to line segment BD. So therefore we have in quadrilateral DBCF that CF is equal to BD as well as parallel. Therefore quadrilateral DBCF is a parallelogram because opposite sides are not only equal but also parallel. So from this we can then conclude again that opposite sides must be equal and parallel. In this case DF, we can say, must be equal to BC, and line segment DF must be parallel to line segment BC. But if we take DE, then we can say that DE is half of DF, because E is the midpoint of DF according to our construction. But DF in turn, we've seen there, is equal to BC. So therefore this then gives us the first part of the proof, namely that DE is equal to half of BC. It's actually the second part as I've put it down here. Furthermore, we know that DF is parallel to BC, but this is the same as to say that DE is parallel to BC, which then concludes the proof. Next we prove a theorem which is a type of a converse theorem to the midpoint theorem. It states that the line segment through the midpoint of one side of a triangle and parallel to a second side bisect the third side. So if we can look at this particular sketch, we have a triangle ABC. We know that D is the midpoint of the one side, in this case AB, and we draw DE parallel to BC. Now we want to prove that E will be the midpoint of side AC. So what is then given is this triangle ABC, with D the midpoint of line segment AB and line segment DE parallel to line segment BC. We need to prove, or it's required of us to prove, that AE is equal to EC. So we carry out the following construction, which is always possible. We construct line segment AF such that it's parallel to line segment DE, and furthermore we construct line segment GE such that it's parallel to line segment BA, and we produce this line segment GE to get to the point F, which lies on the ray GE. So what do we observe? Firstly, we see that quadrilateral ADEF is a parallelogram for the simple reason that according to our construction, pairs of opposite sides are parallel. From this we can conclude that opposite sides must be equal. So in other words, we can, in some way, we don't need to write down everything, that AD is equal to EF. In a similar way, quadrilateral DBGE is also a parallelogram. You can check it again. The reason is because pairs of both pairs of opposite sides are actually parallel. And because DBGE is a parallelogram, we can then conclude that DB is equal to EG, because opposite sides will be parallel. Putting these two last facts together, what can we get? we can start off by saying that we know that FE is equal to AD. But remember that D is the midpoint of AB, so therefore AD is the same as DB. But here we have proved that DB is equal to EG. So if we look at the first and the last one, we can say therefore we know that FE is equal to EG. So what we do now is we compare these two triangles here, namely triangle AEF. We compare that with triangle CEG, and we already have proved now here that FE is equal to GE. That's the first thing. Furthermore, angle EAF is alternately equal to angle ECG, right? Because we know that AF is parallel to BC, and furthermore the two angles here are vertically opposite. So therefore the two triangles will be congruent due to the side angle congruency. Now because these two triangles are congruent, we can therefore conclude that AE, can you see the first and second position, is equal to CE, and that proves then that E must be the midpoint of AC, which concludes the proof. We would like to prove one more important fact, and that is if we have three or more parallel lines, like in this case we have the parallel lines A, B, C, D and EF, makes equal intercepts on a given transversal. So we have the transversal PQR such that PQ is equal to QR. Then these three parallel lines will make equal intercepts on any other transversal. Now if we draw for instance the transversal MNK, then we want to prove that MN is equal to NK. So we are given the three parallel lines which are cut by two transversals PR and MK, and we know that PQ is equal to QR, and we want to prove that MN is equal to NK. The construction is that we draw an additional transversal, namely transversal PK with O an element on line segment QN. How do we prove it? Firstly, we go to the red triangle, triangle PRK, and we know firstly that Q is the midpoint of PR. So in other words, we know that PQ is equal to QR. Furthermore, we know that QO is parallel to RQ, so therefore from the previous theorem we can conclude that O must be the midpoint of the third side, namely PK, or we know that PO is equal to OK. Then we go to the blue triangle and we prove something very similar. Firstly, we know that O is the midpoint of PK. That's been proved. Furthermore, we know that line segment ON is parallel to line segment PM, and therefore from the previous theorem we can conclude that N must be the midpoint of MK. Therefore MN must be equal to NK, and this then conclude the proof. If we utilize the last theorem, then we can look at an example where we can use this theorem to divide a line segment into any number of equal parts. For example, we are given a line segment AB, and we are required to divide this line segment AB into 3 equal parts, or any number of equal parts. Now, one way that you may think you can do it is to measure this, divide by 3, and then find the points M and N, but this is not accurate enough. So what do? Well, the first step is we draw any line segment AF, as long as the angle BAF is an acute angle. Then the second step, with A as a center, we draw any circle or arc, and we determine the point of intersection C, which lies on line segment AF. Then we continue with this process. Now we know that at least the circle will have a radius equal to AC. Then with C as center, we draw another circle or an arc with that same radius AC to determine the point E, and then with E as center, we repeat the process, draw again a circle with a radius AC to determine point D. So now we've got this 3 additional points on line segment AF. So then in a third step, we connect point D with point B, and then through E we draw a line segment parallel to DB, and through C we draw a line segment parallel to DB to obtain the point M. There we've obtained the point N. Then what do we know? From the previous theorem, we know that the parallel lines CM, EN and DB cuts off equal parts from the line segment AD, so therefore it will cut off equal parts from the line segment AB, and that then means that AB will be equal to MN, will be equal to NB. Now this is a useful way of dividing a given line segment into any number of equal parts. You are now in a position to tackle tutorial 4, which deals with the midpoint theorem. So you are given a triangle ABC with angle A equal to 70 degrees, B equals to 60 degrees, and D, E and F, the midpoints of line segments AB, AC and BC respectively. Furthermore, it is given that AB is equal to 6 centimeters and AC is equal to 7 centimeters. Firstly, you need to draw a sketch containing the information here, and then calculate DF, EF and angle FDE. And lastly, prove that the area of triangle DEF is equal to a quarter of the area of triangle ABC. In the second problem, we are given that line segments CD and BE are the medians of triangle ABC, and that they intersect at O. Then line segment AO intersect line segment BC in F and meets the line through C parallel to EB in G. Now this sounds very complicated, and that's why you need to draw a labeled sketch. And after you've got the sketch, then you need to prove that AO is equal to OG, that OBGC is a parallelogram, and lastly that OF is equal to a third of AF. I suggest that you pause the video, do tutorial 4, and then come back and view possible solutions. Let us look at a suggested solution to problem 1.1 from tutorial 4. You are given a triangle ABC with angle A 70 degrees and angle B equal to to 60 degrees. Furthermore, D, E and F are the midpoints of line segments AB, AC and BC respectively. Furthermore, it's given that AB is equal to 6 centimeters, so AD as well as DB will be 3 centimeters or 30 millimeters, and it's also given to us that AC is equal to 7 centimeters or 70 millimeters. Therefore AE is equal to CE, and both will be equal to 35 millimeters. So you need to calculate firstly the length of DF as well as the length of EF and angle FDE or angle 3 as indicated. Now the first two parts are relatively easy. If we look at DF, what do we know? We know that D and F are midpoints. Therefore, according to the midpoint theorem, DF will be equal to half the length of line segment AC, and that is 35 millimeters. And in the same way, we need to find EF, because E and F are the midpoints of two of the sides. EF will be equal to half the length of line segment AB, and that is 30 millimeter. Now we want to prove or find the measure of angle 3. So firstly we observe that angle B is correspondingly equal to angle 1, because remember, if D and E are midpoints, then from the midpoint theorem we know that DE, line segment DE, is parallel to line segment BC. So therefore angle B and this angle 1, which of course is the same as angle ADE, are correspondingly equal, and therefore they both equal to 60 degrees. In the same way, angle 2 is correspondingly equal to angle A, and therefore equal to 70 degrees. The reason here is because DF is parallel to AC, due to the fact that D and F are the midpoints of the two sides. So therefore angle 2, which is the same as angle BDF, is correspondingly equal to angle A, and therefore equal to 70 degrees. But the sum of angles 1, 2 and 3 are actually 180 degrees, because angle ADB is a straight angle. Or we can say that angle 3, or the required angle, namely FDE, is therefore 180 degrees minus angle 1 and angle 2's measure, which is of course means we need to subtract 70 and 60, or 130 in total from 180, and therefore the angle as requested will have a measure of 50 degrees. Let us consider a suggested solution to problem 1.2 of tutorial 4. We need to prove that the area of triangle DEF, the shaded one, is a quarter of the area of triangle ABC. Note we see quite a few parallelograms here, namely quadrilateral ADFE is a parallelogram. I hope you can see why. Because remember, we know that DE is parallel to BC, EF parallel to AB, and DF parallel to AC due to the midpoint theorem. So therefore clearly quadrilateral ADFE is a parallelogram. In a similar way, quadrilateral DBFE is a parallelogram, and quadrilateral DFCE is a parallelogram. So if we if we look at the area of triangle DEF, we know that if we draw a diagonal in a parallelogram, then it will bisect the area. So the area of DEF being half the area of parallelogram ADFE will be the same as the area of triangle ADE. But the area of DEF is also half of the area of parallelogram BF ED, and half of that is also triangle DBF. And lastly, this triangle, the area of triangle DEF is also half of the area of parallelogram DFCE, and that in turn is equal to the area of triangle E or CEF or EFC. So what it really means that all four the small triangles have the same area. Therefore the area of triangle ABC is the sum of the areas of the four smaller areas. So it's 4 times the area of the shaded triangle, because all 4 the triangles we've shown here have the same area, and then if we want to isolate the area of triangle DEF on the left hand side, we need to divide throughout by 4. Therefore it's equal to 1/4 of the area of triangle ABC. Let's look at the suggested solution to problem 2.1 from tutorial 4. Now it is given here that CD and BE are medians of triangle ABC. Now just to recap, what is a median? A median is a line segment drawn from the center of a side to the vertex or the angle opposite that. So if we say CD is a median, that means D is the midpoint of AB. Right. In the same way, if BE is a median, it means that E is the midpoint of AC. So we really know that AD is equal to BD and AE equals to EC. These two medians intersect in the point O. Now we draw line segment AO and produce it to intersect firstly line segment BC in F and the line through C parallel to EB in G. So here is the sketch. So it's very important that you remodel this verbal description in a sketch model. It's much easier to look at the sketch. So we need to prove now that AO is equal to OG. So what do we know? Firstly, we know if we look at the shaded triangle, we know that E is the midpoint of AC that is given, and according to the construction, line segment OE is parallel to line segment GC. Therefore, from the converse of the midpoint theorem, we know that O must be the midpoint of AG, and therefore AO will be equal to OG, which then proves this first part. Let us look at a suggested solution to problem 2.2 from tutorial 4. Here we need to prove that the shaded quadrilateral is a parallelogram. Now note what we already know. We already know that BO is parallel to CG. So if we could prove that OC is parallel to BG, then both pairs of opposite sides will be parallel, and it will be a parallelogram. And that's exactly the way we will proceed. Now, what do we know? We know in triangle ABG that D is the midpoint of AB, and we proved in the first part that O is the midpoint of AG, because we have proved that AO is equal to OG. So D and O are the midpoints. So therefore, from the midpoint theorem, we can say that that line segment DO must be parallel to line segment BG. Now, if line segment DO is parallel to line segment BG, then line segment OC will be parallel to that. Of course, we also know that DO will be half of BG. So this is exactly what I've written here. From the midpoint theorem, knowing that D and O are the midpoints of sides AB and AG, we know that line segment DO is parallel to line segment BG, and that DO is equal to half of BG, which we don't need at this stage. But the important thing is we can say that OC, line segment OC, is parallel to line segment BG. Therefore, the shaded quadrilateral is a parallelogram, because we've proved now here that line segment OC is parallel to BG, and it was given that line segment BO is equal to line segment GC according to the construction. So therefore, we have proved that two pairs of opposite sides are parallel, and therefore it must be a parallelogram. We now look at the suggested solution to the last part of tutorial 4. So we need to prove here that OF is equal to a third of AF. Now, what do we know? We firstly know that OF is equal to a half of OG, because the diagonals of a parallelogram bisect each other. Or if we cross multiply, we can say that OG is twice OF. But we've proved earlier that OG is the same as AO. So therefore AO is also equal to twice OF. We can see that AF is simply the sum of AO and OF. And these can be written in terms of OF, because we've proved that AO is twice OF. So therefore AF is 3 times OF, and if we want to make OF the subject of the formula, we find that OF is AF divided by 3. We have come to the end of the video on quadrilaterals and the midpoint theorem. Remember, you need to consult textbooks for additional examples or other resources. I can think of a couple of resources. There's the Shuttleworth series, which should be at your schools. There's textbooks of various other textbooks writers. There is the well-known answer series. There is the Pythagoras series. And there is a selection of old exam papers. All these can be very useful. So attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in the video. Repeat this procedure until you are confident. Do not forget, practice makes perfect. Good luck and goodbye.